talk about kind of valid uncertainty estimates in these settings. This might be that you usually have a very rich structure of classes, right? So in the medical domain, you very often have different risk categories. You have kind of hierarchies of conditions and symptoms. You usually also deal with kind of rare classes, a very long-tailed class distribution. And then most importantly, a problem that we kind of stumbled over is that very often the crown truth you're dealing with, you're using for training, evaluation, calibration, etc., is actually unknown or uncertain. And this is, for example, illustrated on the right and on the bottom here, where you can imagine that in a lot of safety critical domains, especially medicine, the way we obtain labels for training and evaluation is usually through expert annotators. And in a lot of these domains, tasks are or can be incredibly difficult and ambiguous, leading to disagreement among even very experienced experts. And then the question is, how do you deal with this kind of disagreement, which usually mirrors the underlying ambiguity and difficulty of the task during training, evaluation, and calibration? And in this talk, I'll specifically focus on calibration. Just to differentiate that a bit, in the vision community, of course, we are very aware that a lot of the standard data sets we use and work with are prone to labeling errors, right? So some examples here on the bottom on MNIST and Cypher 10, we know that there are labeling errors. But when I talk about uncertain crown truth or ambiguity, this is actually kind of a much more severe underlying problem, where you could actually argue that this MNIST example, it's not mislabeled, it's just a very ambiguous example. Meaning if I were to ask 10, 50, 100 different people, some of them might always say it's a 5. Some of them might always say it's a 3. So we simply don't have enough observational data to make kind of an informed decision. So that's going to be the topic of today's talk. And just as a rough outline, I'll start with a short introduction to conformal prediction. Conformal prediction is a very nice and lightweight framework to do uncertainty estimation in classification, but also beyond in regression and other tasks. So I'll introduce some notation, some background, and the basic intuition. And then I'll talk a bit about how we can adapt conformal prediction to these settings where we have crown truth uncertainty, how we call it, for example, through disagreeing annotators. And I'll essentially walk through these 3 questions here. The first one being, where does our crown truth actually come from? For conformal prediction, we are explicitly looking at the crown truth we use for calibration. And then what happens if this crown truth is uncertain because annotators disagree? And then, of course, the interesting question from the method side, how can we handle this? How can we adapt conformal prediction to these settings? Okay, so let's get started with some theory here. And let me walk you through the notation. So usually we assume for conformal prediction that we have some predictive model, which I'll call P. This model might depend on some parameters. It might be a neural network with weights. And we assume that this model is kind of trained to approximate some posterior distribution of our classification task. So we want to predict the probability of some label Y being the true label given an input X. Now the task or the framing of conformal prediction is that under high uncertainty, both kind of model and data uncertainty, this is an incredibly difficult task to make kind of a single decision on the correct class. So instead, what we want to do is we want to construct confidence sets of classes, which I'll denote C here, which are a subset of all the possible classes. And we want to do this with a so-called coverage constraint or coverage guarantee, where we can say that with high probability, the true label Y is included in this confidence set. Right? So you can imagine you have a classification task in a medical domain or even on MNIST and Cypher, and instead of predicting a single label, for example, the top one, we predict a set of labels, and the set size should adapt by the uncertainty on the given example. And we want to make sure that across our test, over our test set, kind of marginally across our test examples, we have this so-called coverage guarantee. The nice thing about conformal prediction is that this coverage guarantee can be controlled by you as the user. So you can basically say, I want to have 99.9% coverage, irrespective of the model performance. And conformal prediction is able to give you that performance. Now, of course, there is a counter side to coverage, which we call the inefficiency, right? So trivially, we can always obtain 100% coverage by just including all the possible classes in these confidence sets. So there's a trade-off. We basically want to have coverage 1 minus alpha, but we want to be as efficient with our uncertainty as possible. So we want the set size on average to be as low as possible. So that's the duality of conformal prediction usually. And Another nice property here is that conformal prediction is entirely post hoc, so no training involved, and it has very limited, very minimal assumptions. The main assumption being that we want to have exchangeability of our calibration and test examples. I'll talk about that a bit more later. But in a nutshell, exchangeability is an even weaker assumption than IID examples that we usually have. And this guarantee and the whole framework is entirely independent of the model. You can plug in your neural network, your SVM, your LLM, whatever you care about, and independent of the data distribution. The only caveat here, what I mentioned before, is that the coverage guarantee we get is marginal. So in contrast to, for example, Bayesian approaches, where we usually intend to give a conditional guarantee conditioned on the example X, this is not the case for conformal prediction. The guarantee, the coverage guarantee, will be marginal across our test examples. Okay, to give you an example of how this can be implemented in practice, and this is usually just like a couple of lines of Python or NumPy code, is this very simple split conformal predictor, where we basically have two steps. The first step being prediction. This is what we do at test time. It basically defines how do we construct the confidence set C given our model predictions. And just to be very simple here, we just take the model predictions, which might be kind of our softmax output, or it might be our logits of our neural network, and we threshold them. And we call this the conformity scores. And the conformity score is actually a model choice. It doesn't have to be the softmax output. It can be something more complicated. It can take into account more information, for example. But we assume the conformity score to be higher for a specific class K, the more likely this class is to be the true class. And we just threshold. So the set is just all the classes where this conformity score or kind of the model prediction is above the threshold. Now, the key question is, of course, how do we calibrate this threshold in order to get our coverage guarantee? And we do this very simply by having a held out calibration set. On this calibration set, we assume that we have labels. So we can actually compute the conformity scores E for each calibration example xi for the known ground truth label yi. And then we take a simple alpha quantile of these values, right? So there's a slight correction here, but in a nutshell, if you have very large calibration set, it's essentially an alpha quantile. Now then, by construction on the calibration set, you have coverage 1 minus alpha. And then essentially, statistics tells us that by the exchangeability assumption, by assuming that the test example comes from the same distribution as the calibration examples, we also have the coverage guarantee at test time. So this is how it works in a nutshell. I'll briefly skip this. And here's an example of how this looks, for example, on Cypher 10. We have different conformity scores here. We can for now ignore the RAI2 here. This one is just using the softmax output of a simple ResNet on Cypher 10. The ResNet gets like 82% base accuracy. And we basically use conformal prediction now to elevate this performance to 95% coverage or 99% coverage. And you see what I show here in the table is essentially the average inefficiency. I show on average how many classes are included in the constructed confidence sets in order to get to the specific coverage level of 95 or 99%. And so you see that on average, I need roughly 3 classes in my confidence set to have 99% coverage if my base model gets 82% base accuracy. And these confidence sets, of course, vary by example. And here are some qualitative examples on the bottom. You can see on easy examples like this airplane on the left, the set is rather small. We have coverage. Airplane is actually the true class. On more complicated cases, for example, the third one here, where personally I wouldn't have known whether that's kind of a cat or a horse or whatever, the confidence set gets larger, so it kind of reflects the uncertainty of this example. And in this case, unfortunately, we don't have coverage because I believe the true class is deer. Okay, so this is kind of the basic idea of conformal prediction. So you can really think of conformal prediction as this post hoc calibration layer after training that instead of giving you a single class, it gives you these confidence sets, and these confidence sets are extremely lightweight. They have no or very limited assumptions, but the confidence sets you get out somehow reflect the uncertainty. The confidence set is larger for difficult examples and smaller for less difficult examples or kind of easier examples. And this is why conformal prediction is actually becoming quite popular for uncertainty estimation tasks, especially in decision-making contexts where you have high stakes, as in the medical domain, for example. Now, what we worked on is realizing that the labels we use for calibration doing conformal prediction might actually not be as crisp, as unambiguous as we think. And so in the rest of the talk, I'll walk you through that process of realizing that the ground truth that we usually work with for calibration, but also for training and evaluation, is actually not always kind of certain and fixed, but there's some uncertainty to it and where this uncertainty comes from. And then I'll highlight how we can integrate this back into conformal prediction to get better estimates of uncertainty and improve our coverage guarantee. Okay, so let's ask ourselves, where do the labels that we usually get when we download a data set or when we kind of work with a specific data set in a specific domain usually come from? And if you read a machine learning paper, then in the method section, usually you read statements like this, where you say, okay, we have a training set or a calibration set, and we assume that these are exchangeable or IID examples sampled from our data distribution P. Now, this is, of course, not entirely true, because if I look at this Cypher 10 example, then the first realization is that I don't know the ground truth label. Because A, I wasn't there when the image was taken. I wasn't there when the image was downloaded from the internet. I wasn't there when the image was downscaled in resolution or post-processed in any way, right? So instead, in machine learning, the tools we've developed to solve this task is that we usually gather data, and part of the data gathering usually does not involve labeling. And we do the labeling separately by presenting the data to experts. Now, because this on Cypher 10 is a simple image recognition task, we can think that all of us are kind of experts in visual recognition, especially in this very simple domain where we just distinguish between a couple of animals and maybe truck and airplanes. So if I look at this image, I would say could be a bird, right? And this is exactly what we do for the majority of our data sets, including Cypher 10, including ImageNet, including most of the segmentation data sets, etc. And there has actually been a recent paper that does this exercise for Cypher 10. So the original Cypher 10 was labeled by the authors. And then there was a paper relabeling the Cypher 10 test set using multiple annotators. So here you have 50 annotators looking at the image and deciding which of the 10 classes it should belong to. And you see, I'm not that wrong. There are like roughly 16 people that agree that this could be a bird. But there are unfortunately 23, 24-ish people that say it's a cat. There are a couple of them that say it could be a deer, a dog, or a frog. But the key thing you see is that this is actually not an easy task. Annotators disagree. So now, what we typically do in many dataset constructions is that we simplify this process. We basically assume that there should be a single class for this image. And so we do some majority voting. Or in regression tasks, we take the mean, right? So we simplify the problem into a single label. And in this case, the majority vote would be cat. Okay, so at this point, it's important to realize what we actually have here, right? So I mentioned in the method section of an ML paper, you would see the statement on the top here. We have our labels and examples sampled from the true data distribution. But then if we actually download the data set, in most cases of these data sets, this is not true. The label does not come from the true distribution. It comes from some other process. For example, this majority voting process. So the distribution it comes from is what I call the voting distribution P vote here. And clearly in this example, assuming that the annotators are doing a good job and that they kind of that this is kind of repeatable, that there is no annotation noise, clearly the true distribution, the true posterior distribution that is approximated using these frequencies here is not the same as the voting distribution, because the voting distribution says it's a cat and it's unambiguous, like all the probability mass is on cat, whereas the true distribution might be very different from that if we trust the annotators. So now for conformal prediction, this means that if we want to have a coverage guarantee with respect to this true distribution P, then we have to have labels from P, which we don't have. So the only guarantee we get is with respect to the voting distribution. So if the voting distribution is the same as the true distribution, so that all the labels are crisp, all the label distributions are one hot, then we have a valid coverage guarantee. Otherwise, there is a gap between coverage for the voting distribution and the true distribution. So let me try to illustrate this a bit more, because I think this is kind of a very important distinction for the remainder of the talk. So here's a simple 2D example. It's like 3 classes, red, blue, and green. It's basically 3 Gaussians that are manually placed. You can see that the green one is a bit separate, and the blue and the red one, they heavily overlap. You can imagine this could be an image recognition task or some prediction task. And you can imagine that there might be this third dimension that we don't observe. And across this third dimension, these three classes might be perfectly separable, right? So these in all three dimensions, this problem is a linearly separable problem. Any classifier should be able to solve it. In the Cypher 10 example, for example, you might imagine that if we had higher resolution images, then it might be very easy to say whether this is kind of a cat or a bird. But we don't have this information. We also don't have the true label in practice. So here I just show, for comparison, the true posterior distribution of this problem, which I can compute because these are Gaussian distributions. And you see this kind of smooth transition between the blue and the red here. And you can imagine that our example from before would lie somewhere in here, somewhere between bird and cat. Whereas other examples that are very crisp, that are very easy and unambiguous, might be on the green side, for example, this airplane. Of course, in practice, we also don't observe this true posterior, so this is all hypothetical. So now the voting distribution simplifies the problem. It simplifies the problem extremely. It goes from this kind of strong overlap on the left to a perfectly linearly separable problem. By definition, majority voting makes your problem linearly separable. This also means that this majority voting stage ignores a lot of the uncertainty you have in the data. And you can have a similar argument for other processes, not only majority voting, but also if you take the mean in the regression task, or you vote on kind of your semantic segmentations or something like that. You will always ignore some of the underlying uncertainty. So now, this is, of course, still, as a toy example, it's very hypothetical. So let me give you actually a serious example that you might encounter in the real world, especially in the medical domain. So here's a dermatology task. We are given one image, and we are supposed to predict the underlying skin condition. And this is like we follow the same procedure as before. We look at the image, and now we ask experts to label the image for us. Okay, and here are kind of these 6 different annotations that we get from the different annotators. And because it's a medical task, dermatologists with experience are used to not giving you a single label, but they're used to giving you a differential diagnosis. Multiple possible conditions that are ordered by likelihood. And this is what I try to show here with these kind of braces here. You can see that for the first annotator, this is the most likely condition. Hemangioma is a bit less likely, and melanoma is least likely. So these are essentially rankings or partial rankings of conditions. Now, on this data set, what we used to do is we also used to do majority voting. And of course, majority voting on these rankings is non-trivial, but there are smart people out there that figured out kind of a majority voting algorithm for that. And the majority voted label is hemangioma. And you can see it makes sense, right? I underlined it here. Most of the annotations include hemangioma. Very often, hemangioma is meant to be the most likely condition. Now, you might also notice that this ignores a lot of information. For example, it ignores melanoma. Now, you see in the colors, I highlighted a risk classification. Right? Hemangioma is benign, but it's still classified as medium risk, whereas melanoma is kind of a cancerous condition, so it's a high-risk condition. And usually, this is kind of a condition that in a dermatology screening, we would like to capture and make sure that we can avoid that. So by doing this majority vote, again, we ignore a lot of the underlying uncertainty. And in this case, we actually ignore a serious condition that we would like to check for. OK, so under this premise that our labels usually come from this annotation process, and that we have, in a lot of interesting tasks, a lot of disagreement in these annotations, the question is, can we embrace this disagreement and this ambiguity in conformal prediction? And the core idea here is to ideally use the annotations directly. This is not always possible, especially in the dermatology case, where the annotations are very structured, right? These are kind of partial rankings. There's kind of a lot of information hidden in how the dermatologists come up with these rankings. For Cypher 10, for example, it might be different because each annotator only gives us a single label. So what we come up with in order to abstract away the specific formats of the annotations we have is that we want to work on aggregated frequencies. And we'll later call these plausibilities. So essentially, on Cypher 10, we can directly use the frequencies. And we call this the aggregated distribution. It's an approximation of the true posterior distribution, assuming that you have well-trained annotators, there's little annotation noise, you have good annotation tools, and so on. For our dermatology case, it's a bit trickier because we need to aggregate these different differential diagnoses, these rankings. But as I said, with majority voting, people figured it out. So we also get a distribution over conditions. And here, again, you see that hemangioma is the most likely one, but melanoma is actually very close because it's included in a lot of the annotations and usually also at very likely positions. So now the important thing to realize is that aggregating these annotations in a very raw way is kind of the best option we have in approximating the true posterior. We'll never observe true labels, or we'll never observe the true posterior distribution. So calibrating, evaluating, training with respect to the annotations, to the expert annotations directly, is the best we can ever hope to do in many tasks that we deal with, where it's difficult to actually get real crown truth. And just as an example, in the dermatology case, real crown truth would mean very invasive tests. For many conditions, we would have to cut out skin, we would have to do very elaborate lab tests to figure out kind of the true underlying condition, and even then there might be uncertainty. And of course, we don't want to do this for a lot of cases, so the best we can do is trust our expert annotators and use this kind of information directly. So now, using conformal prediction in this setting, the first thing we have to figure out is, what do we mean by obtaining coverage for a confidence set? Okay, in the classical sense, coverage is a binary outcome. We have one crown truth label, and we check whether this one crown truth label is included in a confidence set or not. It's a simple yes/no question. It's 0 or 1. Okay, if we have ambiguous crown truth and we want to calibrate with respect to these frequencies, these distributions, we have to change that to some extent. And this is where what we call aggregated coverage. And we'll imagine that we have a vector like these frequencies, a plausibility vector. Plausibility basically is a categorical distribution that indicates how plausible a specific label is to be the crown truth label. And there's an example on the right here where we have the plausibilities here. So this is basically the frequencies. So 32% think it's a bird, 46% think it's a cat, and so on. And in the standard coverage definition, we look at the confidence set, which includes cat and dog. We look at the majority voted label cat. We see cat is included in the confidence set, so we have coverage. In our aggregated coverage definition, we essentially look at how much of the plausibility mass of this categorical distribution we cover in our confidence set. So in this case, we have cat and dog in there. Cat gets 46% of the votes, and dog gets 60% of the votes. So together, we get an aggregated coverage of 62%. So in order to get a coverage of 1 in this case, we would actually have to include all the possible labels that annotators voted for. So just to make this a bit more formal, what we essentially want to do is we want to compute this coverage with respect to the aggregated distribution. So we want to kind of assess the likelihood of the true label being included in the confidence set. We can rewrite this as an expectation because it's a binary event, right? If we were to know the true label, we could check is the true label in the set or not. It's a binary event, so we can write it as an expectation. And now the important thing is what the expectation is actually over. So our examples still come from the true distribution P, but our labels now come from this aggregated distribution. The aggregated distribution essentially mirroring our annotations. And then the realization is we can split up this expectation, and then this inner term is what I described as the aggregated coverage on the previous slide. So it's basically looking at the plausibilities for each class and checking, is this class included in the confidence set, and then just summing up. Now, an important realization from writing it down this way is that before, coverage was marginal across examples. If you have 100 examples, you have 90% coverage. You expect that for 10 of these examples, we don't have coverage. For 90, we have. Now, coverage becomes both marginal across examples and labels. Meaning, if we have, for one particular example, multiple likely labels, so for example, as in the example before here, where the plausibility is, for example, heavily split between cat and bird, then the conformal predictor can actually decide how to distribute the coverage between these different labels. And the other realization is, if we can approximate, or if we have perfect annotators, and we were to get infinite ratings, use infinite raters, and assume that this aggregated distribution eventually converges to true distribution, then we can actually achieve coverage with respect to the true labels, even though the true label, the true posterior distribution might be highly ambiguous, so might have high entropy. Okay, just to make this a bit more visual again, On the left, we have the plot that I showed before on this toy example here, where we have devoted labels, clearly simple, linearly separable problem. So I trained a simple linear model on it. I kind of annoyed the model a bit so it doesn't get perfect accuracy. And then what I show on the right is essentially conformal prediction results with respect to the voted labels. So I use these voted labels to calibrate a conformal predictor based on this linear model. And I want the conformal predictor to give me a target coverage of 95%. And I repeat this experiment over and over again with different random splits of my data into calibration and test data. So this is kind of the green histogram you see. So you see that on average, we actually get our 95% coverage. Now, the problem is, on this toy example, I of course know the true labels, and I also know the true posterior distribution. So now if I evaluate coverage in this new kind of formulation of what we call aggregated coverage, with respect to these true posteriors, then my actual coverage in blue is actually significantly lower, which essentially means that by calibrating and evaluating against these majority voted labels, I feel safe. I feel that I get the 95% coverage I get. But if I had access to the true labels, I would actually realize that I undercover by roughly close to 10% here, right? So in a medical setting, you tell your clinicians, you tell your patients, you tell the regulation that you get 95% coverage. But in reality, you only get, 87. Okay, so this is the problem we kind of want to solve. So how can we go about this? And this is actually a very simple approach, is we use these plausibilities, or we can also directly use the raw annotations, and we basically augment our calibration set. Essentially, we repeat each calibration example m times. For each repetition of this calibration example, we sample a new label from the plausibilities. If we have a very easy, unambiguous example, this label will always be the same. If we have high entropy in our plausibility, so there's a lot of disagreement among annotators, we will have different labels. And then we just perform standard calibration on this augmented calibration set. So this sounds easy. The main problem with that is that it invalidates the one assumption that we make in conformal prediction, namely exchangeability. And I won't go into too much detail here, but you can very easily see this by writing down the joint distribution of all our calibration examples and the test example Z, and realizing that we have a structure in this distribution because we know that the first m examples are exactly the same examples with different labels. For exchangeability to hold, you need this joint distribution to be permutation invariant. So however I permute these examples, I need to have the same probability. But this is obviously not the case if I know exactly that the first m examples are the same, the next m examples are the same, and so on. Which in practice just means that we can use this approach, we just don't get a coverage guarantee. So the question is, can we do this and still have a coverage guarantee? And the answer is yes. This needs a bit of calculation, and I'm happy to walk people through if they want to, or refer to the paper. And the main adjustment we need to make is that the quantile computation that I showed earlier is to be slightly adapted, right? So you see that now we have these additional terms with m. Now, of course, with kind of large enough calibration data, this is still an alpha quantile. This is a very minor adjustment, but it establishes that we can actually get a coverage guarantee. The only cost that we pay is that instead of getting coverage 1 minus alpha, we get coverage 1 minus 2 alpha. And this is because we kind of augment the calibration set. As I said, I'm happy to walk people through. For now, I'll skip this. So now the question is, can we go beyond this coverage of 1 minus 2 alpha? And the answer is yes. And this answer is twofold. First of all, in our paper, we show that you can get arbitrarily close to 1 minus alpha if you are willing to split your calibration data into two halves. So if you have enough data, you can get arbitrarily close to 1 minus alpha. However, there's also a lot of promising recent work on doing conformal prediction without exchangeability, which would have direct implication here as well. Now, the question is, do you need all of this? So this is a nice theoretical exercise. And in practice, it actually turns out that empirically, you always get coverage 1 minus alpha. Okay, so empirically, we tried really hard to construct toy examples and to construct like adversarial examples where you actually get this coverage 1 minus 2 alpha, but empirically, you always get coverage 1 minus alpha. Another nice property of this is that without any ambiguity, this approach essentially recovers standard conformal prediction. And it does this on a per example basis. For ambiguous examples, we improve coverage using this kind of Monte Carlo approach by sacrificing some efficiency, right? On unambiguous examples, we behave exactly the same as standard conformal prediction. So essentially, if you want to calibrate directly against annotations, but you're not sure how ambiguous your data set actually is, this is a drop-in replacement, right? You're not losing anything, right? Except for theoretically, you lose a bit of coverage. But in practice, you lose nothing. It's very easy to implement. And it will behave the exact same way as standard conformal prediction if you have unambiguous examples. OK, let me show some examples in the last few minutes here. So these are results on the dermatology data set that I showed earlier. Just to note, by now we also open source this data, not the raw images, but the annotation data for everyone that's interested in that kind of disagreement data. And here I show results for standard conformal prediction, where we essentially calibrate with the majority voted labels. So on the example I showed earlier, you calibrate against hemangioma. And then in blue again, I show the coverage against these voted labels, right? We want to have coverage 72% in black here. And on average, you see that we also get this coverage. And then in green, I show the aggregated coverage against the plausibilities, against the aggregated annotations, essentially. And you can see here that we have an under coverage of roughly 10%. Instead of 72 on average, we get something around 61, 62. And we get this on average by including 2.6 classes in our confidence set. Now, of course, we want to fix this miscoverage here, highlighted in red. And we do this using our Monte Carlo conformal prediction by kind of calibrating directly against the annotations or the aggregated distributions, the aggregated annotations. And you can see what happens is essentially just the shift. The whole histogram shifts to the right. The target coverage is 72%. We now get 72% of aggregated coverage. And then, of course, the voted coverage is more because we are getting more conservative. And this is what you see on the bottom. On average, we now include 4.57 conditions in our confidence set. So this essentially means the difference between the 2.6 and the 4.5 here, this is the cost we need to pay in order to handle the ambiguity that is already in the data. The only thing is that on the left, before, we ignored this ambiguity, and now we are taking it into account, and obviously, this will lead us to being more conservative. So here are some concrete examples again. On the top, the example that I showed before, where on the left you have the plausibilities overlaid by the confidence set in green. For standard conformal prediction, you see the majority voted class here, hemangioma, is included, and some less important classes are included. Using our Monte Carlo conformal prediction, we are still not perfect, but we include especially melanoma as the second most likely class and also a high-risk condition. Then on the bottom, I have particularly difficult examples where we had annotators that apparently couldn't agree at all. There are 5 different conditions. All of them have the same plausibility. And here we also provide a bit more coverage. OK, so in conclusion, conformal prediction or Monte Carlo conformal prediction is essentially conformal prediction based on sampled labels or based on raw annotations that takes directly into account the disagreement you might have in the annotations. And just to repeat, the main insight I want you to take away from this talk is that whenever you download the data set, whenever you construct the data set, it's actually important to think about what labels you want to provide, what labels you are given. In very ambiguous settings, especially in safety critical tasks where this is very common, the labels are very often not representative of the true underlying ambiguity uncertainty because there has been some post-processing, for example, majority voting or averaging. Yeah, and with Monte Carlo conformal prediction, we essentially want to tell the story that we can directly use the annotations and actually benefit from the disagreement in these annotations. Of course, this makes our predictions more conservative, but in practice, this also means that we get kind of more valid and better uncertainty estimates. I also want to briefly highlight that the same principle actually applies to multi-class classification. So with our work, we also establish a coverage guarantee for that, for people that are interested in conformal prediction. And a similar result can be applied to robustness, right? So you can now calibrate with data augmentation and get a coverage guarantee there too. OK, so I'll stop here. There are a couple of links. Of course, feel free to reach out if you have any questions that you see better fit for an offline discussion. But I'm also happy to take any other questions now.